All right, let's get started. So the first section we're covering today, the main things that we're going to be talking about are monotone functions now, and then dealing with when the images of functions are intervals. So first let's talk about what it means for a function to be monotone. It means the exact same thing for a sequence to be monotone. Now it's just a more general definition that works for functions in general instead of just sequences, which are a special type of function. So we got a function from f, or we got a function f from some domain D to R. It's said to be monotonically increasing, provided that whenever you have two elements in the domain u and v where u is less than v, then f of u is less than or equal to f of v, right? So just like with our sequences, if n1 was less than n2, then f of f1 was less than or equal to f of f2. And then it's strictly increasing if we replace that less than or equals with a strict inequality less than. And then we have the same definition for monotonically decreasing would be to flip it, and strictly decreasing would be to flip it. And then a function f is monotone provided it's monotone increasing or monotone decreasing. Any question with any of those?
No.
Okay. All right. So now we're going to get to probably the weirdest proof that we're going to do today. The reason it's weird is because it's easy to get lost in the details of everything that we're doing, to forget big picture what we're doing. So trying to establish very clearly what we're doing, try and give an idea of how we're going to do it, and then go through it. So we're going to prove that if f is a function, f from D to R, so let me say it like this. We're going to show that if f is a function from D to R and it's monotone, and if its image is an interval, then it's continuous. So after we're done with this proof, if you know that a function is monotone and its image is an interval, then the function's continuous. We're just going to handle the case where it's monotonically increasing, and we're going to ignore the case where it's monotonically decreasing, since it would be a similar proof. Does that make sense?
Yeah.
Okay. And what do you understand what I mean by the function's image is an interval? If a function's image contains, forget that picture for a second, but if a function's image contains this point and this point, then it for sure contains every point between.
Right.
It's an interval. Okay. So if it's monotonically increasing, and if its image is an interval, then it is continuous. Then the function's continuous. So we knew that functions, or we already knew that monotone sequences had nice features. Now we're going to see that monotone functions have nice features. Intuition for how we're going to do this? Maybe it's better to go through the proof first, and then come back to the picture to see what we did, and then fill in blanks in case anything doesn't make sense. Because it's overwhelming. Okay, so let's prove this. So let f be some function from D to R such that f is monotonically increasing, and such that the image, f, when you plug in the whole domain, remember that notation for image, is monotonically increasing, and the image of the function is an interval.
Just to clarify, the domain also has to be an interval, right?
No.
Oh.
The domain is just any domain.
Okay.
All we're requiring is that the image is an interval and it's monotonically increasing.
Okay.
Okay. So now, where were we? Next. So let f be one of those functions. Now we need to prove that this seems continuous. That's what we're trying to prove. So we need to grab some sequence xn that converges to x naught and prove that f of xn converges to f of x naught, and we're done. Right? Continuity. So let xn be any sequence in D that converges to x naught in D. Now, we're trying to prove it converges. I'm going to show that its image converges directly. So I'm going to say let epsilon greater than 0, and now I'm going to find the natural number that makes it converge. So let epsilon be any positive number, And it remains to show that if we can find some natural number big N, such that the absolute value of f of xn minus f of x naught is less than epsilon from that index onwards, then we're done, right? So here's what we're trying to show. Now, notice that proving this inequality, proving that the absolute value of f of xn minus f of x naught is less than epsilon for all n as an index, is the same thing as proving f of x naught minus epsilon is less than f of xn, and f of xn is less than f of x naught plus epsilon. Right? You can take this and you can split it into two inequalities. Remember doing that with absolute values?
Yeah.
Okay. So if we can show this is true and this is true from some index onwards, then we're done. Now, once again, we're not going to prove everything. We're only going to show this one because showing this would be very similar. And I can't remember if it's an exercise or not to show the second half of this. But so we're just going to show this inequality from here onwards. Okay, so now we're trying to find some index big N such that f of xn is less than f of x naught plus epsilon from that index onwards. Now we have two cases that we need to handle. Observe that if f of xn is always less than or equal to f of x naught, then this inequality is true for all n. What can I do for you?
Good morning.
Morning.
I just need to get my finger. Are you using this thing?
Oh, no, feel free.
I don't know why they don't return it, but you know. I don't know who uses it.
I'm guessing the physics class does right after.
You are so kind, thank you. And I'm glad you have one student.
Yeah, it's better than just talking
She's
to a
very,
camera.
very lucky to just have you. Thank you, excuse me for interrupting.
Oh, not a problem.
Good to see you.
Good to see you. All right. So notice that if f of xn is always less than or equal to f of x naught, then this is already true for every n starting at n equal to 1. Does that make sense? So one of two cases, either f of xn is always less than or equal to f of x naught, or at least one of them is bigger than it. So if f of xn is always less than or equal to f of x naught, we're done. We found our index, it's 1. Because it's true for every natural number, so then we've shown that this is true. On the other hand, assume that there is some point in the index, some k in the natural number, such that f of x sub k is greater than f of x naught. Okay, so now we got some point bigger than f of x naught. Maybe here's where it's good to jump to our picture and explain what I'm going to do from here because it's kind of weird. So since we know that our function is an interval, since we know that the image of our function is an interval, I now know that f of x naught is in the image, and I know that f of x sub k, for some number k, is in the image. Right? So now I know every point from here to here in between is also in the image of this thing.
Okay.
Right? So here's what I'm going to do. I'm going to let y sub epsilon equal the minimum of f of x naught plus epsilon halves, which is going to be right in the middle here, and f of x sub k. Notice I don't know where f of x sub k is. All I know is that it's bigger than f of x naught. So it's somewhere above it. Could be clear up here, could be right barely above it, could be anywhere above it, but either way, now y sub epsilon for sure is less than f of x naught plus epsilon. That's what we want y sub epsilon to be. We're just trying to find a point in the image that is less than f of x naught plus epsilon.
Okay.
Okay? So it makes sense what this y sub epsilon is, and that it is for sure less than f of x plus epsilon.
I don't actually see where you're going with it.
I know you don't see where I'm going with it. That's what I told you, that it's one where it's easy to lose track of why are we doing this. Yep. So, but we'll try and re-motivate it after we go through it and understand all the steps.
Okay.
But the point so far is now for sure y sub epsilon is between, is between. It's bigger than f of x naught for sure, and now it's less than f of x naught plus epsilon for short.
Right.
What we're ultimately going to do, maybe just like skip ahead in the proof, we're going to find some index such that f of xn is less than or equal to this value from some index onwards, and therefore it's less than or equal to this value from some index onwards, and we're done. It converted. Or then we've shown this half of the inequality right here.
Right.
So this y sub epsilon is something that's for sure less than this, and we're going to get that this is less than or equal to this from some index onwards. Or f of xn is from some index onwards. Okay, but anyway, so we have our y sub epsilon. It's the minimum of these two things. So observe that since y sub epsilon is between these two values, it could be this value, but it's for sure greater than this value. But the point is this is an interval. Since the image of the function is an interval, and y sub epsilon is between these points, then that means if it's in the image, there has to be a point that mapped to it. So there has to be some x sub epsilon in the domain that maps to that. Remember, we don't know what our domain looks like. I don't know that my domain's an interval. So I have no clue. Is it really spotty? But we don't know what it looks like. So I need to, just because I picked some point in here doesn't mean that for sure it's in the image of the function. But since we know that our image is an interval, now I know that there is some x sub epsilon in the domain that maps to y sub epsilon. So later, instead of saying f sub epsilon, I'm just going to start calling it f of x sub epsilon to help keep clear that it's the image of that point. Okay, so anyways, observe that since y sub epsilon is in this interval, and our image is an interval, and since f of d is an interval, then there must be some point in the domain such that f of x sub epsilon equals y sub epsilon. Now, since f is a monotonically increasing function, then anytime x naught is less than x sub epsilon, we know that the image of the function, oh no, we just know that this is the case. Since f is monotonically increasing, then I know x naught is less than x sub epsilon. So I know x sub epsilon is to the right of this point because the function is monotonically increasing. I know that f of x sub epsilon is bigger than this. Therefore, the point it came from has to be bigger than this point because the function is monotonically increasing. The function has to be increasing, and so if I've got a bigger value, it came from a point further to the right.
Can you point out again where you know that that's the bigger value?
Where
we prove that?
So I know that this is bigger. I know this because I know this.
I know, I'm saying where did we prove that?
Oh, this one?
Yeah.
Okay. That was from the picture I was explaining right here. So y sub epsilon is this value, is y sub epsilon. Y sub epsilon is the minimum of these two things. By definition, this is bigger than f of x naught. Right? That was the point that gave us something bigger than f of x naught. We said, assume that there is some k in n such that f of xk is bigger than f of x naught. So I know that this is bigger than f of x naught, and this for sure is bigger than f of x naught. Y sub epsilon is the minimum of these two things. Therefore, y sub epsilon is bigger than f of x naught. Okay, so since y sub epsilon is bigger than f of x naught, then x sub epsilon has to be bigger than x naught because the function is monotonically increasing.
Right.
The only way to get a bigger value is to take a further point to the right. Okay. So, note now that anytime x sub n is less than x sub epsilon, f of x sub n is less than or equal to f of x sub epsilon. This, any index that makes this true also makes this true. Does that make sense since it's monotonically increasing?
Yeah.
So here's where we can start to see the whole proof come together now. Because I know that xn is a sequence that converges to x naught. And I know that this is bigger than x naught. So I know that I'm going to be able to find some index where this is true from that index onwards. Therefore, this is going to be true from that index onwards. Therefore, this inequality is going to be true from that index onwards, and we're done. That's how I'm going to link it all together. Let's link it, and then we'll explain again. So, but does this make sense? This implies this. That implication makes sense?
Yes.
Okay. So since the limit of xn is equal to x naught, then for any positive number you pick, I'm going to pick the number x of epsilon minus x naught. How do I know that's a positive number?
Yeah, just like,
Okay.
why?
So since yeah, that's how I felt over and over again with reading the proof until it clicked in my head. So since the limit of xn is equal to x naught, then there must be some index, some natural number, such that this inequality is true from that natural number onwards, right? Now, we could break up this inequality into its two pieces, take the right-hand inequality, and it reduces to this. X of n is less than x of epsilon from all n onwards. That make sense?
Yes.
Okay. So, since x of n is less than x of epsilon from that index onwards, f of x of n is less than or equal to f of x of epsilon from that index onwards. But by definition, f of x of epsilon is less than f of x. Plus epsilon, sorry.
Will you, wait, oh. Will you show me where you got f of x sub epsilon is less than f of x sub 0?
Yes.
plus
So f of x sub epsilon is y sub epsilon
epsilon?
is at most this value.
Oh, okay, I see now.
And this value, right, because it's the minimum of these two, so in either case you can say it's at most this and it's at most this. So it's at most this. This is for sure less than f of x plus epsilon. So I know for sure that f of x sub epsilon is less than f of x naught plus epsilon. So this is always true. And I just really found an index where this is true from that index onwards. Therefore, this is true from that index onwards. And there's our whole connection. So we just barely found an n that makes this inequality true from some index n onwards. Right?
Alright.
Similarly, we could have found some other n prime, that makes this inequality true, the minus, from some index onwards. We're not going to show that. Then let n be the max of those two indices, and then you're going to have this inequality is true from m onwards. Both of them are going to be true. Put them both together, and you get this. Does that make sense?
Will you explain what you're doing with letting n be the max of those two?
Okay, so I know that this inequality is true from n onwards, and I know that this inequality is true from n prime onwards. Let m be the max of n and n prime, then this is true from m onwards, and this is true from m onwards. And if both of these are true from m onwards, then this inequality is true from m onwards.
Okay,
Because it's just combining those two back together to that.
right.
So, f of xn minus f of x naught is less than epsilon for all n greater than or equal to m. Therefore, the limit of f of xn is equal to f of x naught, therefore f is continuous. Which is what we were trying to show. Think that makes sense? Think you got it? Should we go over it one more time?
The whole proof?
Yeah.
Sure, yeah.
Alright, from the top. So, let f be a function that's monotonically increasing, and let the image of the function f of d be an interval. We're proving that f is continuous. So, let f be the function that's monotonically increasing, and let its image be an interval. Grab xn in D such that the limit of xn is equal to x naught in D. So we know x naught is in D, and we have a sequence in the domain that converges to x naught. Now we need to prove that f of xn converges to f of x naught. So how do we do that? Let epsilon be any positive number, and it remains to show that we can find some index n such that f of x n minus f of x naught is less than epsilon from that index onwards. We're going to break this up into two inequalities. We're going to break it up into f of x naught minus epsilon is less than f of x n, and f of x n less than f of x naught plus epsilon. If we can find some index n where this is true from that index onwards and this is true from that index onwards, we're done. We're going to find what index this is true. We're going to find an index such that this is true from that index onwards. Okay, so observe that if f of x n is always less than f of x naught, then our index is just 1. If f of x n is always less than or equal to f of x naught, it's definitely always less than this, and we're done. On the other hand, assume that there is some index such that f at that index, f of x at that index, is greater than f of x naught. F of x sub k is greater than f of x naught. So f of x sub k, we don't know what it is. It could be above here, it could be below here, but it's for sure above this thing, right? Now, all we're using this f of x sub k for is to find a point in the image which is for sure less than f of x naught plus epsilon, right? We need to find a point in here that's for sure less than this, and we're going to call it y epsilon. And then we're going to show that any time, and then we're going to find an index such that f of x n is less than or equal to this thing from some index onwards, which is going to give us that's less than or equal to this thing. So the whole point of this x sub k is to just find a y sub epsilon that's for sure less than this value. We're just trying to find something in the image less than this value. So we have f of x sub k, but we don't know whether or not f of x sub k is less than this value. But we can use the fact that the image of this function is an interval to get a point less than this value. So I let y sub epsilon be the minimum of f of x naught plus epsilon halves, that's for sure less than that value, and f of x sub k. So it's the minimum of those two things. Either way, it is for sure less than this value. Right? So we know that y sub epsilon is in this interval, is in the domain of the function. And since f of d is an interval, then we know that there must be some point in the domain that maps to y sub epsilon. Right? So we found our x sub epsilon.
I have one question though. So
Yep.
on line 7, we're using the intermediate value theorem, right?
Yes.
Isn't there, it doesn't have to be a special type of function, like maybe it's continuous or something? I don't quite remember the theorem, but.
Well, we're not really using the intermediate value theorem actually. All we're saying is that since the image of the function is an interval, and since y sub epsilon is between 2 points for sure in the image of the function, then y sub epsilon is in the image of the function, so there has to be a point that maps to it. That's what it means to be in the image. So it actually doesn't have anything to do with the intermediate value theorem. It's just a definition of being in the image of a function. You're in the image of a function if there's a point in the domain that maps to you. That's the only way you're in the image.
Oh, I see.
Yeah, okay, good. So since y sub epsilon is in the image of the function, there has to be a point x sub epsilon that maps to it. Right? Okay. So we got that. Now since f is monotonically increasing, then we know that x naught is less than x sub epsilon. How do we know that? Because f of x naught is less than f of x sub epsilon. Right? Okay, so this minus this is going to be a positive number. Now notice also, since this function is monotonically increasing, that anytime x sub n is less than x sub epsilon, then f of x sub n is less than or equal to f of x sub epsilon. And this is what ties the whole proof together, basically, is this implication.
Maybe one second.
So now, here's what ties the whole thing together. I know xn converges to x naught, which is a point less than x sub epsilon. So I'm going to be able to find an index such that from that index onwards, this is for sure true, which makes this for sure true, which is going to make this for sure true from that index onwards. That's how we tie it all together now. So that's why I need to get the x naught in the domain, because I know xn converges to x naught. Okay. So notice that if x sub xn is less than x sub epsilon, that f of xn is less than or equal to f of x sub epsilon. Now, since the limit of xn is equal to x naught, then there must be some index big N such that xn minus x naught, the distance between those 2 points, is less than any positive number we pick. We pick this positive number. How do we know this is a positive number? Because x of epsilon is greater than x naught. So we know that since the limit of this is equal to this, then this inequality has to be true from some index onwards. That's what it means to converge. You can break this inequality into its 2 halves. One of those halves reduces to this. So this is true from some index onwards. We don't care about the other half of the inequality. Now, since this is true from some index onwards, this is true from that index onwards, and we know by definition of our y sub epsilon, or our f of x sub epsilon, this is always true. So I know this is true from some index onwards. I know that this is always true. Therefore, this is true from some index onwards. So we showed that this inequality is true from some index onward, called it capital N. Similarly, we can show that this inequality is true from some index onwards, call it capital N prime. Similarly, there must be some n prime such that this inequality is true from that index onwards. Let m be the max of those 2 indices. If this was true from some index onwards, and this was true from some other index onwards, and m is a further index or the same index as those, then this is true from m onwards, and this is true from m onwards. So they're both true from m onwards, so this inequality is true from m onwards. So we found an index, capital M, such that this inequality is true from m onwards. That's the exact definition of convergence. So therefore, the limit of f of xn is f of x naught, which means it's continuous. Okay, think you got that? Ready to move on to the next one? We should be good, I think. It's this line. Okay, quick corollary of this and an earlier theorem that we did. We're going to combine them together now. So now, let f be any function whose domain is an interval. So let f be a function from some interval to R, where f is a monotone function. Now, notice over here, we just did it for the case where it's monotonically increasing. We could have proved it also for monotonically decreasing. Therefore, it's true for monotone functions. Okay. So let f be a function whose domain is an interval, and that's a monotone function. Then f is continuous if and only if its image is an interval. So I've got a function from an interval that I know is monotone. I'm going to prove it's continuous if and only if its image is an interval. Yeah. I thought I didn't say more than that.
I think, did we just prove that?
We proved one way. Earlier we proved the other way. We're going to put them both together. So assume f is continuous. Then going way, way back, we already proved, it was theorem 3.14, that f sub I is an interval. We proved that if you have a continuous function from an interval, the image is an interval.
Oh.
And you probably remember that one.
Yeah.
Yeah. And then, I think that this was the last theorem we did, not last week, but the week before. And then this is what we just read proved. Now assume that f sub I is an interval. Assume that the image is an interval. Then, using what we just proved, it's continuous. Okay? So now, some nice information that we understand about functions that are monotone and that are using intervals. So if I've got f from an interval to an interval and it's monotone, I now know that function is continuous. Example. Oh, so that's that. Now we're going back to just talking about strictly increasing and strictly decreasing functions, because we're going to need it when we start talking about inverse functions. So we're going to kind of make a leap now and go back to just talking about increasing, decreasing functions, right? So do an example of showing that a function is strictly increasing. So we're going to look at f on the interval. To help motivate this, we're trying to work our way up to talking about functions that look like this, x to the 1/2, square root function. And what's the problem with the square root function? So we know that the square root function is supposed to be the inverse of a parabola, right?
Yeah.
So f of x squared, what does that look like? That looks like a parabola. If you take the inverse of that function, what does it look like? It looks like this, which isn't a function. Right?
Yeah.
So we want to work our way up to being able to talk about functions that are 1/2. Functions like that. And to do that, we need to restrict the domain on the parabola, and then that makes its inverse look like this, which is now a function. So that's what we're working our way up to in talking about inverse functions. And we need them to be, it's easy to talk about their inverses when we know that the function is strictly increasing. So we're taking this function x squared and we're reducing its domain to just the right-hand side, basically making sure that it's a one-to-one function, and it's strictly increasing. So look at f as a function from all 0 and all the positive real numbers to all the real numbers by f of x is equal to x squared. And we're going to show that this is strictly increasing. So I'll let u and v in the domain such that u is less than v. Then u times u is less than u times v, right? I knew that u is less than v, and I know that u is either 0 or a positive number. And so when I multiply both sides by u, then the inequality is still true. Might remember that proof clear back when we were talking about proofs with positivity. Yes, okay. And then, when you take and you multiply both sides by v, that's also true. So I've got u squared is less than u times v, which is less than v times v, which gives me u squared is less than v squared. So it's a strictly increasing function. Anytime u is less than v, then u squared is less than v squared.
And we were able to multiply both sides by u and v because we know they're positive.
They're positive, or if they were 0, if one of them was 0, u is the one that has to be 0. U squared is 0, a positive square root is a positive. It's obvious in the case that it's 0, so we kind of just ignore that case. This isn't a rigorous proof. It's just an example to understand how you would show something strictly increasing. It's more to establish intuition than rigorously prove it. You could rigorously prove it. And then we're going to do a similar thing here. Look at f of x from r to r by f of x is equal to x cubed, not x squared. So notice that a cubic function, we can use the entire domain, and it's always increasing. Thank you. So f from r to r by f of x is equal to x cubed, we're going to show that this is strictly increasing. So let u and v in the domain such that u is less than v. What do we need to show? U cubed is less than v cubed. Another way that we can show that u cubed is less than v cubed is to show that v cubed minus u cubed is a positive number. So v cubed minus u cubed is equal to this times this. Now notice that this is always a positive number because v is greater than u. V greater than u means that this is positive, so this is always a positive number. So if this is a positive number too, then we're good. So since v is greater than u, then this is a positive, okay. If v and u have the same sign, notice v squared is always positive. V times u, if they have the same sign now, is always going to be positive. And u squared is always going to be positive. So in the case where they have the same sign, this is for sure true. If v and u have different signs, then the only way that that works is if u is negative and v is positive. And then a negative cubed is still going to be negative, and a positive cubed is still going to be positive, so this is always true. And then if v or u is 0, then this is obviously true, because if v is 0, then you have 0 is greater than a negative number. If u is 0, then you're going to have 0 is less than a positive number, and so it's true. Not explicitly writing out all the cases, but I think you see how this function is obviously strictly increasing.
I see how it's strictly increasing. I just, for line 2 and 3. Oh, okay.
So we did it a couple different ways. We said we're using the fact that this difference is positive when they have the same sign, and then we're going directly to showing that this is true when they have different signs.
Okay, so you only use.
I'm only using this for the case where they have different signs.
That makes sense.
Okay, yeah. Probably should have broken it up into cases cleaner than just private numbers. Anyways, any question there?
No.
Okay, and so we're going to move on to fix our problem with our x squared, and ultimately the problem was the function wasn't one-to-one, but let's give a definition of one-to-one, even though you've already had this definition 100 times, and I think both Levi and Deshaun you have too. But either way, let's just get it. I don't want to bother moving it more right now. We'll just leave it there. Okay. Right here, definition of one-to-one. So a function now, f from d to r, is one-to-one, provided that for every y in the image of the function, there exists one and only one x in the domain of the function, such that f of x is equal to y. Right? The way that I always think about it is that if f of a is equal to f of b, where a and b are points in the domain, then a is equal to b. So a function maps the same inputs to the same outputs. A function is one-to-one if the same outputs come from the same inputs. So the outputs being the same implies the inputs are the same. If that's always true, then you've got a one-to-one function. Now we're going to define our inverse function. So let f be a function from d to r be one-to-one. Then for each y in the domain, since there exists one and only one x, or sorry, for each y in the image, then there exists one and only one point in the domain such that f of x is equal to y. We can call that x now. Since there's one and only one, we can come up with a way of marking it, and we call it x equal to the inverse of y. So what do we mean by f inverse of y? We mean that f is a one-to-one function, and x is the one and only one point in the domain such that f of x is equal to y. That's what we mean by f inverse of y. It's a unique point, so this is well defined now. That makes sense? Okay, and so inverse functions have two nice properties that we're going to use over and over again. The inverse of f of x is equal to x for any point in the domain, and f of the inverse of y is equal to y for any point in the image. The functions undo each other. Right?
Yeah.
Okay. So now, let's look at some features of this cubic function. So let f from r to r by f of x is equal to x cubed. First off, notice that f is a continuous function, right? How do we know it's continuous? We proved all polynomials are continuous. Since it's a polynomial, we know it's continuous. We know that f is monotonically increasing, and the domain is an interval. The domain's an interval, and we showed over here, roughly proved, but showed over here that it's increasing.
you're saying, the real numbers are intervals from negative infinity to infinity?
Yeah, what does it mean to be an interval? It means anytime you contain 2 points, you also contain every point between those 2 points.
That makes a lot of sense.
Yeah. So, yes, this R is an interval. Now we know that x cubed is monotonically increasing since we know that it's monotonically increasing. That's what we showed over here. It's strictly increasing, so it's monotonically increasing, right? We know that the image of the function is an interval.
How do we know that?
Because it's a continuous function whose domain is an interval.
Right.
So that's this corollary right here. F from an interval to R is continuous if and only if its image is an interval. So I know the image is an interval because I know it's continuous. Okay? So now I know that the image is an interval, but then the question is, how big is the interval? I'm going to really quick roughly show that the interval is unbounded, and therefore it has to be all real numbers. The entire real numbers is the only interval that's unbounded. Does that make sense?
What are we trying to prove here?
We're not proving anything, we're just listing properties of this thing. We're working our way up to trying to define something like x to the 1/3. That's what we're working our way towards.
Okay.
So we're just listing out some nice properties that this thing has so that we can define this thing and see the nice properties that it has as well. And that it behaves exactly how you already know a cubic function or a cubed root function behaves.
Okay.
So for any n you choose, f of n equal to n cubed, that gets arbitrarily big. And f of negative n, notice n and negative n are both going to be in the domain since the domain is all real numbers. And f of negative n gives us negative n cubed. So f, the image of this thing, can't be bounded from above, can't be bounded from below. So it's an interval that's not bounded from above, and it's an interval that's not bounded from below. Therefore, the image of this thing has to be all of R. Make sense? Okay. So now, looking at the inverse of the thing. F inverse then of f of x is the same thing as f inverse of x cubed has to just equal x for all x in R. Similarly, f of x inverse of y is just f inverse of y cubed. Notice we replace the f function with the cubic. Is just equal to y for all y in R. So that's exactly how we're going to define this y to the 1/3 thing. We're going to define it to be the inverse, f inverse of y. Where f inverse is the inverse of this f of x function. And notice that our f inverse function is a function from the real numbers to the real numbers once again. And it's also going to be a continuous function. We're going to prove that it's continuous in general when we restrict its domain. But this was just going through an example of defining one of these things, and then we're going to do a theorem and define these things in general. So it was just to get you comfortable with talking about the inverses of x to some natural number. Okay. So let's move on to our actual theorem now. So if f is a function from an interval to R, and it's strictly monotone, meaning it's strictly increasing or strictly decreasing, then its inverse function is a function from f of I to R. Its inverse function is continuous. That's what we're going to prove.
You're using I, or is that?
I is always an interval.
Okay.
So f is from an interval to the real numbers, and we know it's strictly monotone. If we know that about it, then we know that its inverse is continuous. So here was an example where we knew that this satisfied these properties, so this function down here was continuous.
And we know that f of I is also an interval, right?
We do know it now. It wasn't given to us in the problem, but that's using a theorem. We know that this is continuous, And we know that its domain is an interval, therefore its image is an interval.
Okay.
Anyways, so let f be a function from some interval to r such that f is strictly monotone. We define d to be the image of the function, and now we're going to look at the function f inverse from d to r, because this is the function that we're trying to show is continuous, right? Okay. Since f is strictly monotone, then f inverse is monotone.
Why isn't it strictly monotone? F inverse?
F is strictly monotone, which makes f inverse monotone.
Okay.
If output of A is bigger than output of B, then A is bigger than B. If f of A is bigger than f of B, then A had to be bigger than B.
I'm just saying, is there a function where f is strictly monotone and f prime isn't strictly monotone? Just
F inverse?
yeah. I'm wondering why you said monotone instead of strictly monotone.
Oh, because it's all we need. It is strictly monotone, but we just need the fact that it's monotone. Because anything strictly monotone is monotone. I see why you're confused. Yeah. So, since f is strictly monotone, then f inverse is also strictly monotone, but it's for sure monotone. And f inverse of d, we know, is an interval, right? Because f is the inverse of this function.
I get that we know it's an interval, but can you show me how you got that it's I, specifically I?
Because f inverse is the inverse of f. F maps from I to R. F inverse does the inverse of that. It's going to map from the image of this thing. It's going to map from f of I to I, which is a subset of R, so we can still write it this way. By definition of an inverse function, f inverse of it is going to be I. F inverse of its domain is going to be the domain of the function that we started with.
Alright.
So, we know that f inverse is a monotone function, and we know that its its image is I, because the domain of f is I, so the image of f inverse is I, which is an interval. So f inverse is a monotone function whose image is an interval. Therefore, it's continuous. Make sense?
Mm-hmm.
Nothing weird? Theorem 3.23, that's one that we just proved today, right? Yeah. First thing we proved.
I thought we were using the corollary.
Now, first thing that we proved is that if you have a monotone function whose image is an interval, then it's continuous.
Okay.
So f inverse is a monotone function whose image is an interval, therefore it's continuous. Okay. So now we're ready to talk about these functions in general. So consider f from just the positive numbers now by f of x is equal to x to the n for any natural number n. Good so far?
Mm-hmm.
And now we're just going to list some of the properties that we know that this function has. We know that f is continuous, because that's always just going to be a polynomial. We know that the domain is an interval, because that's an interval. We know that f is strictly increasing. This always gets bigger and bigger for bigger values. It never stays the same. We know that the image of this thing is an interval, and that it's actually this interval, because we can get 0 out of this thing, and we can get arbitrarily big things out of this thing. Since its image has to be an interval, then it has to contain all the numbers from 0 to arbitrarily big, so it's going to be this interval. So then we know that the inverse of these functions is going to be from that same interval to R, and it's going to be continuous. That make sense?
No. Your very last line of your first dash.
This?
Yeah, how did you get it was continuous?
So F inverse is going to be strictly monotone. Oh, sorry. F is strictly monotone,
Okay.
and it's from an interval. Therefore, its inverse is continuous.
Oh.
So that's how we know it's continuous. And now we know that it's continuous and its domain is an interval because its domain is the image of F, which is an interval.
Okay.
So now, anytime you have a function that looks like this, you know that its inverse function looks like this. And they're both continuous. Right? So now we can talk about F inverse of f of x. Well, that's just going to be F inverse of x to the n. We know that's just x for all x greater than or equal to 0, or for all x in our domain, same thing. Similarly, F of F inverse of y is equal to F inverse of y, all to the n is going to equal y for all y greater than or equal to 0. Notice that that's our image. So now we're ready to define this. We now define what do we mean by y to the 1 over n. We mean that inverse function of y. And it's defined for all y greater than or equal to 0. So now we know what this symbol means. And now we can also define x to the negative n. What do we mean by that? We're just going to define that to be 1 over x to the n. We know what we mean by this, so now we can just define this to be this as long as x isn't equal to 0. And now we can start using these exponent functions exactly as expected. Need to move the camera again. Wow, we made good progress. I didn't think we'd get through it that fast. Zoom in on just the whiteboard. So now we've got that. We can use exponential functions. They're defined. We can start to use them the way that we know and love. For homework, you're going to prove these two things. They're just both going to be inductive proofs. And you can probably see how they're going to go fairly easily. Base case, x times n times x is the same thing as x to the n plus 1, right? And then assume x to the n plus k, or x to the n times x to the k is equal to x to the n plus k, and multiply both sides by x, and you're done. So that's real easy proof. And then you just use this proof to prove this proof, right?
Okay.
So those are both pretty straightforward. And now we have those properties. So now what we're missing is, now we need x to a rational number. That's the last thing that we need to find, because we know exactly what it means to do something like 8 to the 2/3, right? We know that's equal to 4, for example. And so we know exactly how to deal with these rational things. Let's capture how to deal with them and get what we know and love. Okay, so definition now. For x being a non-zero number, and for why are we requiring it to be non-zero? We don't want to try accidentally taking square roots of negative numbers, for example.
Okay.
Because if we let it be anything, then we could do something like -2 to the 1/2. Uh-oh. That doesn't work. So that's why we're requiring x to be a positive number. Why aren't we letting it be 0? We don't want to try giving a definition of something like 0 to the 0. Okay. So for x being a positive number and some rational number r, where we're always going to make the denominator positive. So notice I can always express a rational. If a rational is positive, then both those numbers are positive. If a rational is negative, I can just require the top thing to be negative and keep the denominator positive. So I just want to keep my denominator positive. So for x greater than 0 and r being a rational number where n and m are integers with n being positive, so keep the negatives in the numerator, we're going to define x to the r to equal x to the m to the 1 over n. Makes sense, right? Now we know that with rational numbers, m times k over n times k is equal to m over n. So we want to make sure that x to the m to the 1 over n is the same thing as x to the k times n to the 1 over k times n. So in other words, we're going to do a quick proof that things like 8 to the 2/3 is exactly equal to 8 to the 4/6. In other words, we can actually think about this as a rational number. We don't have to think about this as an operation on a function and this as an operation on a function. We can start to just think about it. It's x to a rational number, and you can treat that thing just like a number. Up here, we proved that we can multiply them and add them together. Now we need to show that we can treat it just how we treat any rational number.
I'm just a little confused because you said off to the side, we know that m times k over n times k is equal to m over n. And now you're saying we're going to prove it?
We're not proving that this is true. We're proving that when you have these things in the exponents, that also works. And so you can treat these exponents, because remember what this is. This is actually a way of encoding a function, and this is a way of encoding its inverse.
Oh. Okay.
And we need to make sure, can I still just treat those like they're numbers? And that's a piece of what we're handling here. We handled a piece up here, now we're handling a piece over here.
And you're saying we're allowed to use that piece of information that you wrote up there? N times k?
Yeah, we know that this is true for numbers, but now we're not talking about numbers. We're talking about, is it true when I have x squared and we have its square root function? Is x squared square root really the same thing as just x to the 2 divided by 2 equal x to the 1? Are those the same? Okay, it happened to be true in that case because we know x squared then inverse it just gives you back x. So it happened to work in that case, but does this always work?
Okay.
That's what we're proving. And it's just straightforward proof using the properties we have up there. We know that x is equal to x to the k to the 1 over k, right? Apply a function and then take its inverse, you get back where you started. That's always true. Then x to the m is equal to, sorry, missed parentheses there, x to the m. And then we know that we can think about when we have the exponents to powers, we can treat them like times. We know that times is commutative, so we can change the order and we can eventually rewrite it like this.
Okay.
And then now we're going to take then x to the m to the 1 over n. So we know x to the m is the same thing as this thing. Now x to the m to the 1 over n is x to the m to the 1 over n is, we know how to multiply those, and now we're done.
Okay, I see that we rely heavily on our homework problems.
Huh?
So we relied on our homework problems to prove this. So if we're considering like x to the power of something, like an inverse function of some sort, or if it is, like you said, we couldn't just use basic algebra. We have to use the homework problems, but didn't we just use basic algebra to prove the homework problems?
Didn't we use basic algebra to prove the homework problems?
Like, and the proof that we did, you're
In
proving that you
the
did-
homework problems, all we use is the fact that x to the n is equal to the product from x, or from I equals 1 to n of x. This is the only thing we presuppose in proving these things.
Okay. In that proof, you're trying to prove that we can just treat them like we would usually in algebra. Like, you can treat the numbers normally, but then in the homework problem, we treat the numbers normally,
So yeah, in the homework problem, we treat the numbers normally. Here, we're proving that the same numbers, you can reduce the numbers exactly how you expect in algebra. That this is actually equal to this, because we don't, how do I know that I can apply the same cancellation when it's like this? I use the fact that I proved that these things can be treated like algebraic numbers, and then we're just showing it.
Okay.
I don't know. I feel like I'm missing your question.
Well, I get caught on the idea that you can't treat them like normal algebraic numbers, and then I'm wondering where that stops, because it seems like we can in the homework problem, but can't in this proof.
We don't in the homework problem. We're proved that we can in the homework problem, and then we use the homework problem. In the homework problem, we're explicitly proving that x to the m plus m is equal to x to the n times x to the n.
Yeah,
And so now when I have those exponents, I know that that's the same thing as just adding them together. I shouldn't have said that you can't treat them algebraically. That wasn't a good way to say it. Just proving that they have the properties that you know exponents have. I don't know another way to say it. We didn't explicitly have defined what that symbol was before. Right? We just had what that symbol was. And is that really the same thing as that? Yeah, obviously with this definition.
I thought we were supposed to prove it inductively, but by like multiplying both sides by x and stuff. And if you're doing that, you're treating them like normal algebraic numbers.
Yeah, they are normal algebraic numbers.
I thought those were functions and stuff.
Well, they are functions, but their exponents are naturals. I still feel like I'm missing what you're saying. When you prove this homework problem, your base case is going to be exactly that x to the n times x is equal to the product from I equals 1 to n of x times x is equal to n of them. And so that's going to handle your base case. You're going to assume it's true for k, show it's true for k plus 1. And that's going to handle this one. And then you're going to use this as a base case when you're proving this one.
Alright.
And then this is just showing, can I reduce my exponents with irrational numbers? Yes.
Okay.
And then finally, showing that these things are always continuous. So the last thing is, we know that x to the n is always continuous. We know that x to the 1 over n is always continuous. The question now is, x to the r always continuous? Right?
Yeah, x to any rational number, but don't we have to like restrict the domain or something?
Yeah, sorry. I'm assuming that we're restricting the domain
Okay.
to 0 to infinity, exactly the way that we had listed over here.
Of x sub n? Or of x sub r?
Like this.
Okay.
So the function f from here, oh, I missed to r. Oops. To r, comma, f of x equal to that. Can't believe I missed that. Anyways, yeah, so I'm saying when this is a function from here to r, and when this is a function from here to r, we know that they're continuous. The last question is, what about if we've got it to a rational? So if I have, just write explicitly, if I have x from 0 to infinity, from that to r by f of x is equal to x to the r, where r is in Q. Is this a continuous function?
Okay.
That's the last thing that we need to prove, and now we can start using exponents the way that we know that we can use exponents. So let r be some rational number, and let f be this exact thing, some function by f of x is equal to x to the r. And we're proving that it's continuous. And we're going to use this by showing that composition of continuous functions is continuous. An older proof that we did a while ago. So since r is rational, then there must exist two integers m and n, such that r is equal to m over n with n positive. Then f of x is equal to x to the m to the 1 over n, right? That's what we meant when we said x to the r. It was an encoding of this. Now notice that this is two functions. This is a function x to the m, and then it's the inverse function of x to the n. So let g be the function by g of x is equal to x to the m, and h be the function by h of x is equal to x to the 1 over n, and observe that f is equal to h composed with g. Or in other words, or it's equal to that since what is f of x? That's equal to x to the r, that's equal to x to the n, over n, that's equal to this. That's exactly what we meant by h, and that's exactly what we meant by g, and they have the same domain, so they map the same way, they have the same domain, they're the same function. So f can in fact be expressed as these two functions. These two functions we know are continuous, so f is continuous since h and g are continuous. The composition of continuous functions gives us a continuous function.
Okay.
And that's it for exponents. So we can go ahead and take a break there while I erase this and start with the next stuff. And also move my charger, plug in my phone in case it dies. Wow, we have double time to spare. So I don't think the next section is very difficult. Plug that in. I'm good, but thank you. just continue?
Yeah.
You can keep going if you want. I'll just start if you're ready.
I'm ready.
Okay. So next we're going to be talking, the next section is limits. We're going to be talking about limits of functions, but first we need to talk about the concept of a limit point. You're already used to, since you took calculus, the idea of the limit of a function as it approaches a specific value x. So that's what we're going to work up to in this chapter, but first we need to start out with the idea of a limit point of a set. So if you give me some set D, a point x naught is said to be a limit point of D if and only if there exists some sequence in D minus that point such that the limit of that point is the limit of that sequence is x naught. So if I can find a sequence xn that doesn't use x naught but converges to x naught in D, then that point is a limit point of D. So x naught is a limit point of D. Remember, the limit point is with respect to a set. So x naught is a limit point of D if I can find a sequence xn in D that converges to x naught, requiring that the sequence never actually uses x naught.
Is it right to say that D could have multiple limit points or an infinite amount of limit points?
Yeah, so let's look at a really simple example real quick. So let D be the open interval 1, 0. So 0 is a limit point of this. Here's a sequence in D that converges to 0 and is never actually uses 0. Notice that 0 is not in D, so the limit point does not have to be in the set to be a limit point of the set. Another example, the limit of 1 minus 1 over 2 to the n is equal to 1. This is a sequence always in D. 1 is a point not in D. But every point in D is also a limit point of D. Pick any number from 0 to 1. You can also find a sequence in this interval that converges to that number and never actually uses that number. I just wrote 2 really quick. So 1/2. 1/2 is a limit point of that. Here's a sequence that's never quite 1/2. That gives us 1/2. 1/3 is the limit point of that. Here's a sequence that's never quite 1/3. That converges to 1/3. I just did over 10n to make sure we never get outside of there. Just make sure we're just incrementing small numbers.
You'd have to choose a different 1 over 10n if it was, if say you were trying to converge to like 9/10 or something.
Yeah, the closer I get to the border, the bigger I need to make this denominator.
Okay.
Yeah, that's true. But we know that we can do it for any number you pick.
Right.
So we're not proving that every point here is a limit point. We're just giving you intuition for what limit points are. So what are the limit points of 0, 1? These are the limit points of that. 0, 1, the closed interval. Those are all the limit points of that set. And a limit point is also a concept that can come up in topology. Anyways, so there's some intuition for what limit points are. I think you have an intuition for it now. So now let's do some proofs. Let's prove that every real number is a limit point of Q, the rationals. So if the rationals are your set, what are the limit points of the rationals? All the reals. That's what we're going to prove. So what do I need to do? I need to show that for any real number you give me, I can find a sequence of rationals that converge to that real number, but never uses that real number. Right? And we know, and obviously what we're going to use here is the fact that Q is dense. Remember what it means for Q to be dense?
Not exactly.
It means that for any open interval you choose, we're always guaranteed that there's rationals in there.
Okay.
That's what meant to be dense. So, 1. Let x not be any point in R, it doesn't matter what it is. 2. Since Q is dense, then there exists, we'll call it Q sub n, in the interval x0 plus 1 over n, since that, say it this way. Maybe I'll, yeah, just going to erase that. Since Q is dense, then for any natural number you choose, for all n in n, comma, exists Qn in Q such that Q sub n is in the interval x naught to x naught plus 1 over n. Okay, that's a good way to say it. Right? For any natural number you choose here, I can always find a rational number in this. That's supposed to be rounded. So for any natural number you choose here, I can always find a rational in this interval. So when this is 1, I know that there's a rational in this interval, call it q sub 1. When this is 2, I know that there's a rational in this interval. Maybe it's the same q, maybe it's a different one, call it q sub 2, etc. So we just created a sequence of rationals, right? Then q sub n, the sequence q sub n that we just constructed, then q sub n is in q minus x naught, right? We never used x naught. I don't know if x naught is a rational or if it's not rational, but either way, q sub n is definitely not x naught and it's always rational. So, Qn is a sequence in this set, and the limit of Q sub n is equal to x naught.
That I do not get. How'd you get the limit of that sequence as x naught?
For any n I pick here, Q sub n is less than that, is within less than that of x naught. What does it mean to be in this interval? That means, so for Qn to be in this interval, what does that mean? That means the absolute value of Qn minus x naught is less than 1 over n.
I'm just not getting the algebra there. How you got from Qn inside the interval to that
Okay.
interval that you have.
Let's be more explicit. I know that x naught is less than q sub n is less than x naught plus 1 over n, right? So, x naught minus 1 over n is then going to be less than q sub n is less than x naught plus 1 over n.
Yeah, I see it now.
Okay, so then we subtract and we get negative 1 over n is less than q sub n minus x naught is less than 1 over n. And then that's exactly what we mean by the absolute value of Qn minus x naught is less than 1 over n. So then for any epsilon you choose, I can obviously make the sequence less than epsilon from some index onwards, because I can make this as small as I want.
Right.
Right. So, makes sense that Qn converges to x naught? Okay. Hopefully it makes sense to Levi and just showing you too. Let's see. Oh, we're done. That's all we're trying to prove, right?
Wait, what?
We just barely showed that x naught is a limit point. I guess I could say therefore x naught is a limit point of Q. Therefore, x naught is a limit point of Q.
Okay.
Because that's what we were trying to show.
Right.
We were trying to show that the limit points of Q are all real numbers. We just really showed that for any real number you pick, I can find a sequence of rationals that don't use that real number, but converge to that real number.
Okay, you said something a little bit different. You said the limit points of Q are all real numbers.
Every real number is a limit point of Q.
Okay.
So if we said, what's the set of all the limit points of Q? It's the real numbers. Make sense? Okay. And similarly, we can prove that the limit points of the irrationals is all real numbers, because the irrationals are also dense in R. Notice that the only thing that we needed to use here is the fact that Q was dense in R. So if Q is dense in R, then that means its limit point is all of R. So now those are two logically equivalent things. I don't know if the author bothered stating that, but now that's an if and only if. A set is dense in R if and only if its limit points are all of R. Not if and only if. We didn't prove if and only if. We just showed that if it's dense, then it's for sure, then its limit points are all of R.
Right.
We didn't show the other way around. And I don't know if we're going to. Because now we're going to move on to the limit of a function. So given a function, definition, I don't like how it says it, but I'll just write it so I don't have to think about another way to do it. So given a function, given a function f from D to R and a limit point x naught of D, comma, for a number L and L because it's going to be the limit, we write, he always writes his implications backwards. We write the limit as x approaches x naught of f of x is equal to that L, provided that whenever x in D minus x naught converges to x naught, then the limit as n goes to infinity of f of xn is equal to L. Good proof, but that's the definition. So let's wrap our head around this real quick. I don't really like how he says it. Maybe come up with a better way to say it while we go over it. So we now want to talk about, maybe motivate this a little bit, and how these limit points are useful with an example. Let's look at the function really quick. Let's see what would be x squared minus 1 over x minus 1. Looking at this function. And we're just going to say for all real numbers except for 1, you can't plug 1 into this function, right? You can plug in every other real number. What does this function look like? This function looks like, let's see, we've got 1, there, didn't draw very good, but it's going to be this line with a hole at 1. So the function isn't defined at 1, but that's what the function looks like outside of 1, right? So notice that 1 is not a point in the domain of the function. But we still want to be able to talk about, even though this function doesn't really have a value at 1, the next closest thing is, well, if you could give it a value, what would the value be? What's the natural value to assign to that thing? And that's going to be the limit of the function as we approach that point. And so that's what we're defining here, is we're defining, we're coming up with a way to handle the case where the point isn't in our domain, but but there's still a natural value to assign to that point, even though it's not a value of a function. So it's a way to handle functions with these holes in them, is one of the things that this enables us to do. So that's why when we talked about a limit point, we said the limit point isn't in the domain, but not necessarily, it can be in the domain, but it doesn't have to be in the domain. But the sequence of points that we use never actually use that point. So we're going to be able to take a sequence of points that get closer and closer to one, but never actually use one. And then the image of these points then are going to get closer and closer to this value, but never actually use that value. And these points are going to converge to the natural value that we want to assign there, even though the function doesn't have a value there. So here's what we're saying here. So we have some function from D, and we want to talk about the limit of the function at some point x naught. The limit of the function at some point x naught. So we're saying that the limit of the function at this point exists. The limit of the function.
Good morning.
Lovely. What can I do for you?
I'm just wondering if we've tested everyone that would like to test.
You did?
I was gonna test.
Well, then, are you coming?
Feel free to
Is
go.
this a good
It's
time?
red for me.
Yeah, it's fine. I can keep filming for you. We'll come back to it.
Would Mr. Timpson like to test?
I've already had it. So let's go back to the limit of a function at a point. So given a function f from d to r and some limit point of d, x naught, then for some number L, we say that the limit as x approaches x naught of f of x is equal to L, provided that whenever xn is a sequence in D that doesn't use x naught and converges to x naught, then the limit as n goes to infinity of f of xn is equal to L. Side note, prior to this lecture, anytime we've been talking about the limit of a sequence, we were being lazy because this was really the limit as n goes to infinity of a sequence. So this is what we meant by a limit every time we've written that. Now I'm going to start specifically writing that because now we have two different ways of taking a limit. So we're defining a new way of taking a limit, the limit as x approaches x naught, and we need to define it in terms of the limits that we already know as n goes to infinity. So the limit as x approaches x naught of f of x exists or is equal to some number, provided that whenever xn is a sequence in D that doesn't use x naught, but converges to x naught, then the limit as n goes to infinity of that sequence is equal to L. So if this is true, then this is true. So here's how I wrote down here. The limit as x goes to x naught of f of x is equal to L if and only if the limit as n goes to infinity of f of xn is equal to L, where x naught is a limit point of xn. Well, no, that's not quite right. Where xn is a sequence that's never equal to x naught, but its limit is x naught.
Okay, I think I understand it.
Anything weird? I think it's better to think about it this way. So if I have some sequence that converges to x naught and happens to never use x naught, then whatever that sequence converges to, we're calling the limit as x approaches x naught.
Okay.
So now it's like we're thinking about in terms of our sequence instead of our index. So we're taking the limit as our sequence gets closer and closer to x naught, instead of the limit as our sequence as we get further and further in our sequence. So in the next chapter, it's going to be a somewhat common theme that sometimes we want to think about the limit this way, sometimes we want to think about it this way. So we're going to be proving something that looks like this, and we're going to think, let's think about that in terms of sequences, and come and start talking about it this way, and do the proof this way, and say, and so therefore this, and vice versa.
Okay.
So we need to get somewhat comfortable going back and forth between thinking about these limits these two ways. This is the limit as we get further and further in our sequence. This is the limit as our sequence gets closer and closer to its limit point. Okay. And you'll notice how close this definition is to the definition of continuity. What does it mean for a function to be continuous?
It's continuous at every point.
A function is continuous at a point x naught if, when a sequence converges to x naught, then the limit of this image of the sequence converges to the image of the point. Right? So we say, for x naught in D, then f from D to R is continuous at x naught, if and only if, as x approaches x naught, f of x is equal to f of x naught. In fact, chances are, when you did calculus, this was your exact definition of a continuous function. A function is continuous at some point x naught in the domain, if and only if the limit as x approaches x naught of f of x is f of x naught. Right? Because what's another way that we can rewrite this? The same thing as the limit as n goes to infinity of f of xn is equal to f of x naught, where xn is not equal to x naught and the limit of xn is equal to x naught, right? So that's what this is. So if this being true is the same thing as this being true, which is continuous. So here's another way that we can think about a function is continuous. What does it mean for a function to be continuous? At a point x naught, it means that the limit as x approaches x naught of the function is just the value of the function at that point. Right. Okay, so now let's do some examples using these. Let's find the limit as x approaches 2 of this function. Now notice that this function, well, let's think about what this function is for a second. So we have a polynomial over a polynomial, and then we're square rooting it. We know a polynomial function is continuous. We know a polynomial over a polynomial is continuous. And we know that square root is continuous. Function composition gives us it's all continuous. Right? And notice that 2 is in the domain of this function.
Right.
So the function is continuous at 2.
Okay.
So we know that the function is continuous at 2. We're looking for the limit as x approaches 2. Well, if the function is continuous at x naught, then the limit as x approaches x naught of f of x is just f of x naught. So it's just what you get when you plug in 2. So it's real easy to find the limits of functions at points if the function is already continuous at that point. It's only when the function is not continuous at the point that we have to be somewhat clever and tricky. So this one is very straightforward one. What's the limit as x approaches 2? It's the value of the function at 2. Very straightforward. Here's an example that's more convoluted. What's the limit as x approaches 1 of x squared minus 1 over x minus 1? Notice now, 1 is not, we're assuming for all these functions, make the function as big as you can. Include all the real numbers where the function gives you a value. So, what's the domain of this? It's all real numbers except 1. 1's the only thing that you can't plug in here because we can't divide by 0. So, the limit as x approaches 1 of this thing now, okay, now we're in trouble. We can't just plug in 1, otherwise we're trying to divide 0 by 0. Obviously, we can't do that. But this is going to be the same thing as the limit of x minus 1, x plus 1 over x minus 1. And then you can cancel those out. And now we have a function, x plus 1, that is defined at 1. So just plug in 1, you get 2. So this is the typical way to do it. Now we're actually going to do a proof that this is the case. But in our work when we're dealing with these, chances are this is how I'll usually write it out. But we could write it out explicitly proving it with limits that we know how to calculate. So now we're going to prove this. Prove that the limit as x approaches 1 of x squared minus 1 over x minus 1 is equal to 2. So let x n such that x n is never equal to 1, and the limit as n approaches infinity of x of n is equal to 1. Take some sequence that converges to 1. Then what's the limit of this whole thing? Well, you break it up exactly how you expect. Then we can break it up into a product of things. This is just 1. And we know how to take the limit of this because we know the limit of xn is 1. And the limit of 1 is just 1. Together that's 2, 1. We just get 2. And we're done. Nice, straightforward. So this is how you prove it, but typically, basically when we're done with this chapter, from here on out, when we calculate limits, we're just going to write it out like this. We're not going to bother with going to xn. Typically. There might be cases where it's more useful to do that in the abstract, but when it's a concrete one like that, it's pretty easy to just calculate. Anyways, let's do another one. So the limit as x approaches 8 of x minus 8 over the cubed root of x minus 2. Prove that the limit of this thing is equal to 12. That's what we're trying to show. Notice that 8 is the only point not in the domain of this function because the cubed root of 8 is 2. 2 minus 2 doesn't work. So do the proof. Let xn be some sequence such that xn is not equal to 8 and the limit of xn is 8. So then the limit as n approaches infinity of x of n minus 8 over the cubed root of x sub n minus 2. Well, we can just rewrite that. We can rewrite xn as xn cubed root cubed, and we can rewrite 8 as 2 cubed, right? So now we have a difference of cubes, so this is equal to the limit as n approaches infinity of, factor this out, So we can take out an x to the n to the 1/3 minus 2, and that's going to leave us with x to the n to the 2/3 plus x to the n to the 1/3 times 2 plus 2 squared, right? So now, that all over x to the n to the 1/3 minus 2. Same thing, I'm not going to write too many steps. This cancels out with this, so now that's equal to the limit as n approaches infinity of xn to the 2/3 plus xn to the 1/3 times 2 plus 4, we won't bother writing 2 squared. What's this equal to? Well, we know that the limit of a sum is the sum of the limits. We know that starting with this one, this is going to be xn squared times xn to the 1/3. The 1/3 is going to give us an 8. No, not an 8. Maybe write one more step here. This is going to be the limit as n goes to infinity of let's see, xn, we'll write it this way. Should have probably done it this way. Xn to the 1/3 squared plus xn to the 1/3 plus, we'll split it up into bigger ones. Plus, rewriting this one, 2 times the limit as n goes to infinity of xn to the 1/3 plus the limit as n goes to, well, plus 4. We know the limit of the constant is just 4. Or is just constant. 4, right?
Right.
And now, what is the limit of this thing? Well, we know that xn goes to 8, then you take the cube root of 8 is 2, squared is 4, and then this is 2 times 2 is 4, and then 4 is all up to 12, which is what we were trying to show. Right? Okay. I'll write each of these out, but I don't know that we need to prove them. You can decide whether or not they need to be proved, but let's at least explicitly write them out.
Could you explain 2 more things?
Yeah, oh yeah,
So
sure.
I feel like I'm making a jump to the knowledge, like from my previous calculus class. And I should be, like, can you explain that definition and that note one more time?
Explain this definition.
Yeah, I feel like I'm just making a jump over it because I understand what you're doing over there without completely understanding that.
Okay, so we've got a function. We've got a function, and we'll think about a hole in the function for now. So the function is not defined there. So x naught is a point where the function is not defined, it's defined everywhere else. So given a function f from d to r, and a limit point x naught of d. Notice x naught is a limit point of the domain, even though it's not in the domain. Okay. And some number L in this case is going to be the value here, L. So given a function f from d to r and a limit point x naught of d, for a number L, we write that the limit as x approaches x naught of f of x is equal to L. So as x gets closer and closer and closer to x naught, then the limit as x approaches x naught of f of x is equal to L. Notice we can't just say is equal to f of x naught. Why can't we say that?
Because it doesn't exist.
Because that doesn't exist. So this is how we would typically say it if it did exist. But we just say L because in this case it's not quite there. It's just we get really, really close to it. So we said the limit as x approaches x naught of f of x is equal to L, provided that whenever xn is a sequence in D minus that point, so not including that point, so whenever xn gets closer and closer to x naught, then the image of xn gets closer and closer to L. The image of xn gets closer and closer to L. So we've got xn are these points, and f of xn are these points. So, as xn gets closer and closer to x naught, then f of xn gets closer and closer to L. When x naught is just a point in the function, then L is just going to be f of x naught, right?
Right.
And so when L is in the function, or when x naught is in the function, then we say it's continuous at that point. So if the limit of a function is equal to a value, and that's the value of the function, it's continuous at that point, which means we don't have a hole. And it looks like that. Good?
Yeah.
Okay. So now there's some properties that these limits have, which are the same properties that the other limits have. And you just prove them using the fact that the other limits have them, but we'll write them out. So and I guess we can say what theorem is this? This is theorem 3.36. Let f be a function from D to R. Let f be a function from D to R, G be a function from the same domain to R, comma, and let x naught be a limit point of D such that the limit as x approaches x naught of f of x is equal to some number k, and the limit as x approaches x naught of g of x is equal to some number b. So we have two functions that have limits at x naught. Then, what are we trying to prove? We're trying to prove that the limit as x approaches x naught of f of x plus g of x is equal to a plus b. The limit as x approaches x naught of f of x times g of x is equal to a times b, and the limit as x approaches x naught of f of x divided by g of x is equal to a over b, where g of x is never equal to 0. It's the exact same things that we already have with our limits of sequences. The sum of the limits is equal, or the limit of the sum is equal to the sum of the limits. The limit of a product is equal to the product of the limits, and the limit of a quotient, as long as the denominator behaves nicely, is equal to the quotient of the limits.
It seems like in order for us to subtract the functions and take their limit, we'd also need to know it's like the negative of a function. If you take the limit of the negative of a function, then it's the negative of that limit.
So another one would be that the limit as x approaches x naught of some constant c times f of x is equal to c times the limit of that, which is a.
Oh, okay. Yeah, that makes more sense.
And once again, you use the fact that we know that we can do this with limits of sequences to prove all these, right? We already know this is true when we're doing limits of sequences, so you just rewrite this in terms of limit of sequence, do it, then rewrite it back this way, and you're done.
Okay.
So, do you think we can see any of those? You want to see one of them? I don't know.
Yeah.
Is it as obvious as I think, or?
Let's do one of them in case it's a homework problem.
All right, we'll do one. So, we'll do proof that the limit, proof that the limit as x approaches x naught of f of x plus g of x is equal to a plus b, where f and g are defined how we have it up here, right? So, 1. Let x in d minus x naught such that the limit of xn is equal to x naught, right? Okay. 2. Then the limit as n approaches infinity. We also need to encode that we're given this is true. Well, maybe we'll just use it as we go. So then the limit as n approaches infinity of f of xn, of f of xn plus g of xn is equal to, now we know that the sum of the limits, or the limit of the sum is the sum of the limits, right?
But we also need to know that each one of those limits exists. Don't we? Before we can split them up like that?
We need to know that each one, okay, so you can say if the limit exists, then it's going to be the limit as n approaches infinity of, I don't know why I didn't use curly braces, f of xn plus g of xn. The limit of g of xn. The limit as n goes to infinity of g of xn. Now, it only, if it exists, then this is what it is, right? But what is this? This is exactly what we mean by the limit as x approaches x naught of f of x. That's exactly what this is.
Right.
Plus the limit as x approaches x naught of g of x, but we already know what those are. A plus b.
Okay.
So that's how you prove each of these. That's what I mean. It's very straightforward. Just rewrite this limit as one of these limits. Then use the rule that you need to use. Then write it back as these limits. And you're done. I mean, for doing the product, all you literally have to do is replace that with the times,
Right.
replace that with the times, replace that with the times, replace that with the times. And then for a quotient, same thing, except for you need to specify where g is never 0.
Okay.
So, our limits work exactly the way we expect them to. Okay, one more theorem, then we're done. So, no questions about any of this? Not curious at all?
Nope.
Okay, let's see what we're trying to prove. For a function, suppose x has limit quantity. Oh, we're just showing that you can use function composition basically. So, theorem 3.37? 3.37. Okay, so for functions, we have f from D to R and g from U to R. Suppose x naught is the limit point of D. Suppose x naught is the limit point of D such that the limit as x approaches x naught of f of x is equal to some value, we'll call it y naught. And that y naught is the limit point of U. That y naught is a limit point of U such that that's like a capital U.
It doesn't seem like you're able to just suppose y naught is a limit point of U. But you're saying.
We're taking it by assumption. So we're saying when you have x naught in f, and the limit as x approaches f naught is a point in U, call it y naught, or a limit point in U at least. Maybe it's not in U, but at least it's a limit point of U, y naught. So we're assuming that we have the function that behaves this way.
Oh, okay.
Oh, that was part of what I do next. So, and that y naught is a limit point of U such that the limit as y approaches y naught of not f, what was my other function? G of y is equal to L. Then when you compose them, moreover, supposing a lot of things for this proof, I'll say and we need that what this maps to is a subset of what this maps to. So, and f of D minus x naught, in case it's in there, is a subset of G of U minus y naught. Y naught doesn't have to be in there, it just has to be a limit point. Okay. Then we're finally going to say G composed with f, or the limit of this, is L. Then the limit as x approaches x naught of, how do I want to do that? Of G composed with f of x is equal to L. So, I feel like what it's saying is pretty obvious, but you just have to assume a lot of things to say it. So, the limit as x approaches x naught of f of x is y naught, and the limit as y approaches y naught of g of y is L. Then when you do g composed with f, that function is going to go from, as x approaches x naught, it's going to go to L. And we just need the domains. We need the image of f to be in the domain of G so that composition is even defined. notice the points that we're using. What are the points that we're going to be plugging into this function?
The domain of f.
We're going to be plugging, well, we're plugging in some sequence as it gets closer and closer to x naught, but is never actually x naught. So what could we be potentially plugging in to prove this? We could be plugging in anything in D, but not x naught. For sure, we're never going to use x naught. And what does that give out? It needs to for sure give out everything in U, but it doesn't necessarily need to give out y naught. There could be a hole here, in other words.
Okay, but you said that f of D minus x naught needs to be a subset of the domain of G. Isn't that like the image of G that you have written there?
Oh, yes, and that is not what I should have. Thank you. That would have been very confusing. Is a subset of U minus the set containing y naught. Okay, that makes more sense. Yes.
For sure.
Everything F maps needs to be in the domain of what G is going to map.
Okay.
Okay. Except for obviously the limit point, because there could be a hole in the function at this point. That's not a problem. Okay. So let's prove this. Okay. So I won't write all the words. We'll just write the thinking for it. So the limit as x approaches x naught of G composed with f of x is the same thing as the limit as x approaches x naught of G of f of x is that how I want to say this? Or do I want to do it with f first and then come back? Let d be that, set yn equal. So start out with some sequence. 1. Let x in D minus x naught such that the limit as n goes to infinity, since we have two limits now, such that the limit as n goes to infinity of xn is equal to x naught. Now we're trying to prove that this goes to L. We'll create a sequence y sub n. Let yn in U where each yn is equal to f of xn. So we're just going to relabel these f of xn's yns. Then the limit as n goes to infinity, as n goes to infinity of yn is going to be the same thing as the limit as x approaches x naught of f of x, which we know is equal to y naught, right?
Right.
So yn is now a sequence in U which converges to y naught. And notice it's in U minus y naught. Minus the set containing y naught. And how do we know that it's never y naught?
I want to say it's because of the domain restriction that we put on.
Yeah, we know know that the image of this thing, the image of f, is a subset of this thing, which doesn't contain y naught in there. So whatever xn is, since xn only comes from this, and f satisfies this requirement, everything it maps has to be in here, but not in there. And this is everything that it maps.
Okay, I have one question though. So on line 3, is it also true to say that the limit as n goes to infinity of yn is equal to the limit as n goes to infinity of f of xn?
Yeah, this is f of xn.
Right.
Yeah.
I'm trying to make it fit within the definition of limits. Just so I understand completely how you went from one to the other, but I do not. So.
Yeah, I'm just trying to make very explicit that yn is going to be a sequence in U that converges to y naught, but is never y naught. I could have left all my yn as just f of xn, but the author specifically switches it, and I think he's trying to make very explicit. Look at what exactly the sequence yn is. Okay. Then the limit as n goes to infinity of g of yn is going to be just the limit as y approaches y naught of g of y, which we now know is equal to f. This and this are the exact same thing as long as yn is a sequence that converges to y naught, but is never actually equal to y naught.
Okay.
So,
Wait, how did we know that yn converges to y naught but is not equal to y naught?
yn is in here,
Oh. Okay.
and then here's where we show the limit of yn is y naught.
Alright.
So then we finally got the whole thing. So then the limit as n approaches infinity of g of f of xn is the exact same thing as the limit as x approaches x naught of g of f of x. And we just really showed that this one is L, so this one has to be L.
Okay. Actually, on line 5, how do you get that first limit equal to the second limit?
What is the definition of this? It's this, as long as xn is never actually that x naught, but converges to that x naught.
Oh, right, because in that function, D is the domain and xn is the
Yep.
domain. Okay. Okay, I see now.
Okay, so that was the last major theorem. The author does one more example, and then that's the end of the chapter. Looks like we might have time to spare. We'll leave that up there in case we need to reference it, and we'll just put the example over here. So, let's see, what's the last example that he's doing? Suppose that f is a function from the real numbers to the real numbers such that the limit as x approaches 0 from the composition property of limits, it follows that if k is any natural number, that is true, and moreover, if c is any natural number, that is true. seems kind of weird that he's doing this. Maybe he's motivating you, right, for derivatives. So he's just pointing out some stuff that will explicitly write what he's saying. So let f be some function from R to R such that the limit as x approaches 0 of f of x minus f of 0 over x is equal to some number L. So let f be some function such that when you take this limit, you for sure get a number. Then he says, from function composition, what does that give us? Then we know that the limit as x approaches 0, plug in another function, x to the k for x, so then f of x to the k minus f of, when you plug in 0 to that, you still get 0, over x to the k is going to equal L. Let me think, why is that still L? By function composition. From the composition property of limits, it follows that if k is any natural number, then he's right. Okay, here's why. So I know that the limit as x approaches 0 of x to the k is equal to 0.
I'm here to get Levi's test.
Levi's test.
And then I'll take it home to him at lunch.
Okay, let's see. For Levi. Not that. So he needs this. He needs that. And he needs, let's see if I have any homework of his. I don't have calculus homework, do I? I don't think so. I think that's it. So just us. Thanks. Okay. Where were we? Okay. So, put my marker. Okay. So notice that the limit as of this is for sure 0, right? So now, I'll just call this thing y. So then, I know that whatever this is, if I say y is equal to x to the k, then I know that the limit as y approaches 0 of the limit as x approaches 0 of y is equal to 0, right?
Yeah.
Okay, so basically, as x goes to 0, this thing still goes to 0. And so, it's still the same limit.
I see.
Okay. It feels weird to say it, but
It makes sense.
okay. And now, what else does he show? He says also the limit as x approaches 0 of f of c times x, where c is some constant, minus f of 0 over c times x is also going to just be L, because as x approaches 0, everything still approaches 0. Notice f just had the property. As long as when these two things go to 0, then you get L. So we still have two things in there. We're just writing x a different way. We could write it in terms of y if we wanted, but it still works. And then finally, the last one he writes is that the limit as x goes to 0 of f, if we only put c in here, c of x minus f of 0 over x. He says that this is equal to the limit as x approaches 0 of f, says it's equal to, oh, I see what he's doing. Okay, c times the limit as x approaches 0 of f of c times x minus f of 0 all over c times x, which is now equal to c times L. So he says, now he's saying, notice that if we take the function and we multiply it by a constant, we could have pulled that constant, well, that's just the same thing as multiplying L by a constant. Now how do we get from this line to this line is the trick. The trick, multiply top and bottom by c, c times anything, you can just pull that out.
I got the second part of your explanation, but not the first part. Like, when you're talking about c times
So
x.
now this is a different one. So now what are we showing? We're showing that if you put c just in this part. So up here we put c in top, and we put c inside the function, and we put c down here, right?
Yes.
Now he's saying what happens when we just put c here.
Oh, and then you said you can just pull c out. And it's-
Well, when you put c here, c's still there, but now we multiply top and bottom by c,
Oh.
and just pulled this one out of the limit. But now we already know that this is just L, so now it's L times c.
Okay.
And that's what his last example is saying. And that's everything. So that's the end of 3.7. That clock's not still an hour off, is it?
I don't think so. No, it's not.
Okay. Whew, scared me for a second. Okay, yeah. So that's it. The rest of the class we can use however you want. But you can stop the recording and start uploading the video.